All right, part two of gravity, week five, physics online. We left off talking kind of how Newton's law of universal gravitation works, that it is a proportional to the masses of each object, any two objects, no matter what they are. And then it is inversely proportional to the distance squared. That's the key. It is an inverse square relationship that takes place. So distance has a bigger factor than either mass does. And notice this little sign here is just proportional. It's not exactly equal to multiplying the masses and dividing by the distance squared. There is a constant that we have to put in there. So that universal constant is capital G. Notice lowercase g we use for the acceleration due to gravity, and that's 9.8 meters per second squared. At the surface of the Earth, we find out that changes. The acceleration does, based on how far away from the center of the Earth you are. But we need this universal constant that Newton calculated and then was later confirmed by Cavendish. But we get it to be a number. It's got to be small because we know the gravitational force between two small masses is not small enough to overcome friction. To make two pencils on a table slide together because of gravity coming together, they can't overcome the friction because it's such a small force. So this G has to be extremely small. And we find it to be 6.67 times 10 to the negative 11. That is a constant. It's what you're always going to use for the problems that you work on in this chapter. So anytime the capital G, you need to know the masses of the two objects that you're talking about, and you need the distance between them. In your problem, it's going to end up being the radius, I believe. Radius of the planet would be the distance we're talking about, or the radius between the sun and whatever planet you're talking about. But they'll give you those in the problems, what that distance is. If we look at, and this is that inverse square law, that you have the gravitational force at the surface. As you start to move away from the surface, farther away from the center of mass of the Earth, you actually have 1/4 of the gravity. And if you get three radiuses away, it ends up being 1/9 and so on. That's the inverse square law. We find it throughout physics, not only in gravity, but in electrical fields. We find it in light intensity. All of those things kind of follow this inverse square law throughout physics. One of the things in the objectives, we had what's going to happen as you go if you were to look at the gravitational field inside of a planet. As you go down, if you were to bore a hole all the way through the Earth and you want to fall down, as we always used to say as kids, I'm going to dig a hole all the way to China. If you could do that and go all the way down, you'd find out that this lowercase g, that's at the surface, your acceleration is 9.8. But if you get to the center, your acceleration due to gravity is actually 0. And that's because you're being pulled, the center of mass is being pulled in all directions. And they kind of cancel each other out, just like we did with vectors. And if they cancel each other out, there is no force. And if there is no force acting on you, you have no acceleration. So that's one of the things we look at. And if you're halfway between the center of the Earth, and then you'd have half G and vice versa. It's proportional. Which means weightlessness is not a true thing. You always have weight, or if we want to think about weightlessness, it's just weightlessness is your response to the pull of gravity. So when we look at weight, we said weight was mass times G. Well, if G is 0, technically you have no weight. The other way you can look at that is if it has the absence of a support force. So if you're in an elevator and it's not moving, you have your normal weight if you're sitting on a scale. If that elevator goes up, remember, your inertia wants to stay put, so you have a greater weight. It's being pushed down more. It's that centrifugal force, as we talk. It's kind of a surreal one. But you would have greater weight because your inertia wants to stay put and the elevator is moving up. The opposite would be like if the elevator is going down, it's not going to have as much. You're going to weigh less because you're going in the same direction. And then if we were to cut the cord and the elevator just drops, there would be no support force holding you, so you'd have no weight.